Okay, hello everybody. Today we will talk about normal mode analysis. So what is normal mode analysis? So this is a quick tutorial on normal mode analysis, and I want to show you my quick tool to infer macromolecular movements. So macromolecular movements without molecular simulations, without without MD simulation, without molecular dynamic simulations, which you need compute clusters for and graphics cards and whatnot in order to get enough compute power. So here I will show you basically how you can derive a quick overview of, let's say it like this, molecular trajectories on a two-core machine, as my little laptop here is, and get a rough idea about how a molecule moves just out of its structure. So how does this work? So first of all, what are normal modes? So the normal modes, they rely on this Hessian matrix of a molecule's potential. Yeah, so you have basically potential, which is like your force field. And we will talk about the Hessian matrix, how we can go there, and basically you can decompose movements into what is called eigenmodes. Yeah? So this, like, if you have a building, it has like these eigenfrequencies and eigenmodes, or generally any structure if you're into mechanics, and you can do this also for molecules and calculate basically the eigenfrequencies that a molecule can have. A macromolecule, yeah, so this is here for macromolecule applications basically. So you do this with PDB files, with proteins, with something like that. You can also do this with DNA molecules and things like that, but here in these special applications we do it for proteins. And so how does this work? So you get this second order potential here. So this is a potential approximation. So we have a potential. So this potential is basically the force field. Yeah? So if you have a molecular force field, we will talk about this here. We will use a very simple force field and it still works. So you will see that basically the shape of the molecule determines the possible motions that this molecule can have, protein can have. This is a rough estimate. This doesn't really, let's say, help you to get away without doing MD simulations. But this is a rough estimate and works for let's say it for simple cases, or not only simple cases, but it gives you an estimate on how your molecule will move just from its shape. Okay, and what does this here? So second order approximation, so basically you have your potential and you develop it. So this is just, let's say, the Taylor series expansion, so this first term, second term. Okay. And the story here is that everything lies in this matrix here. So this is the Hessian matrix if you do normal mode decomposition. Because, well, of course you can have higher terms, but we forget them. And this here and this here will be 0. So these QIs are basically the coordinates, so the degrees of freedom. So you have 3, I goes from 1 to n is 3. 3 times the number of atoms, because you have 3 degrees of freedom by atom. Okay, by carbon alpha atom in our case. We will talk about this later on. And so you have your potential, which is basically your force field. You derive this here, and this here is this Hessian matrix, and this is where the big deal here lies in this normal mode analysis stuff. Why? Because, okay, you can choose your potential. If you're a physicist, you know this, or whatever. You can choose your potential to start at 0. So it's just a gauge effect. You can just put your potential to a reference value and say, okay, here I'm at 0, and then you either go up or down, and this is basically the potential energy difference then between where you are. So I can set the first term to 0, bam, gone. The second time I can set it to 0 because I can say, well, I'm in a position, or my molecule is in a position where it is at some kind of equilibrium state, so which means it's in the minimum of a potential well. Yeah? So if you have a potential quit, something like this, and you're in there, then the first derivative should be 0. That's the basic idea. If you at minimum the potential for the potential, so this derivative here cancels out and the 0, and so all the rest here is then the second term here. Yeah, and this is where magic happens. We want this Hessian matrix. So this here is called the Hessian, this second derivative that you have here. Yeah. And so the question is, of course, well, if we calculate what should this V here be? Yeah? So in general, this is a force field like this OPLS force field or Gromos force field or whatever you find in typical molecular dynamics suite. So you can use, for example, Gromex in order to calculate these normal modes. Here we show a way faster but also effective approach. Yeah? So this is just the first view of how a molecule can move, into what kind of direction it will move. Yeah? And we are using something which is called this Avaran and Tyrian approximation. Yeah? So if you go into this paper, so we just use this also with C alpha atoms. So if you click here, and we look into this paper here, so this is a paper which was written in 1998 by Daniel Van Avram and Monique M. Tyrian, and they show here for these actine rods and whatever that they can do this normal mode analysis in the way we do it here, so that it's just basically what happens here, but it's just basically to show that you can use just springs between carbon alpha atoms. This is really magic. Just these springs between carbon alpha atoms, and basically the shape of the molecule tells you into what kind of directions it will move. Yeah. Okay. Magic. Huh? You will see in practice how this works. Yeah? It's like, I don't know, if you have a rod, yeah, then it can bend like this, it can torse like this and stuff like that, and with molecules it's basically the same. So if you have a rod-like molecule, well, it can torsion, bending mode, torsion mode, yeah, first bending, second bending, yeah, like if you, yeah, okay, yeah, you get the idea, yeah, normal modes, okay, yeah. That's the way it works out. And so what we will use is just like a spring potential, and it's enough, yeah, to obtain, let's say, approximate movements of a molecule. So spring potential, yeah, you remember spring potential, yeah, it's the spring constant here. This is the equilibrium distance. This is some difference from this distance, and if you go closer together, yeah, okay. That's the way it works. The spring constant here basically tells you how much force if you get out of equilibrium. Yeah? Nothing special. Yeah. Okay. So you can calculate the Hessian of this. So you can basically derive to all the coordinates, degrees of freedom that you have here. Yeah, in this little tool here, and then you get to something like this. Yeah? So you can calculate this out. You do your R and put it QQ whatever in there, QI whatever, and then you get to this. This here is written like in 3x3 matrices. You have this LM index here, so which goes from 1, 2, 3, yeah, and so if you write it like this is because I implemented this in the computer code. That way is like you have like little block matrices that are 3x3 matrices, as you have like 3 degrees of freedom by atom, yeah, and then you fill in these little block matrices to fill up your Hessian, yeah? And of course your Hessian just has IJ and all together, but I've written this with this LM so that I have these little 3x3 matrices that fill up my Hessian. if you write it down like this, nothing too complicated. This is the form of the Hessian. Yeah, so it's like this. It's one coordinate with the other coordinate here in the inner product here, and of these two vectors, and so you get these little 3x3 matrices here out of this. Okay, and this is basically the distance between the two atoms, and these are basically the x, y, z coordinates of L and M. That's the way it is. Sorry for the notation, but I hope you got it. So 3x3 matrix for x, y, z position for each atom, carbon alpha atom in our case, because we just do this for carbon alpha atoms. And you will see it's even enough to get the shape of a macromolecule, to get its movement out of it. A very rough approximation, but it works very effective. Okay. So calculation of the normal mode. So we have this Hessian matrix, and once we have this Hessian matrix, we solve this eigenvalue problem here. And as we solve this eigenvalue problem, we have these eigenvectors u here, which are called the normal modes, and we have several things here, so which are very important to know. So 1 over lambda, so this eigenvalue basically gives you the frequency, and the frequency of the movement is the square root of lambda of this eigenvalue. And so as the frequency goes higher, you have more energy and stuff like that. And so basically how much energy goes into each mode or something like this is basically with this 1 over lambda here, so that you know basically how much energy is attributed to each mode if you heat up the system, something like this. Okay, and so then we get to this normal mode trajectories here. I know we are pretty fast, but we want to go to the practical idea so that you see the program and how you can use this and how you can get practical here. I hope we're not too fast. I hope you still understand what you're doing, but basically that's what you do. And then you can, of course, from that you can derive some trajectory. So you can say, okay, you forget the mass here. The mass is 1 in our case. So this is a very rough approximation. You can use the mass. We programmed it with the mass for different applications. I will show you that I've written stuff about that, but it's not that important. So the mass is 1. This here is the amplitude. These are basically the components here of this u vector. So you have, of course, you have IU vectors and you have k components. This here is written wrong. I see this here, but the k. Okay, and then you have basically frequencies. And okay, I did this with k. So then this is the ith component of the k vector with the k frequency. So the frequency is the root of the eigenvalue. It's written down here, corresponds to the square root of the eigenvalue of the phase. We forget about it because we just want to have the movement, which phase it is. We don't superimpose the eigenvectors and we forget it. Just want to see the movement and stuff like that. Okay, so to sum it up, so it allows us to get a rough estimate of the macromolecular conformational space, because we get all these eigenmodes and we can say, so this moves like that, it can move like that. It can be directly calculated from the structure without further simulation. So all we need is a PDB file. 3 parameters. The parameters that we put in there are basically approximated for us. It's the amplitude that we want to have, a cutoff value, because we have this here, this spring potential here, and I mean it's a question how many springs we build. We want each atom to be have a spring with each other atom, but only in a certain radius. So if the other atom is very far away, we don't want to have a spring to this other atom. Okay, that's the second parameter. What's the third parameter? The third parameter, so amplitude, cutoff, and how many modes we basically want to output. Of course, you're not interested into all modes, so there is this energy distribution law here that we have here. So we have like 1 over lambda, so big lambda, big energy absorption, whatever, we'll never get there. Okay, so we are interested in the modes that get very easily excited. Yeah, okay, perfect. Okay, so let's try this out. We have this PDB file here, so this PDB normal mode analysis. So we click here, and here's my little tool that I've written a very long time ago. It only runs on Intel processors again, because this has some optimization inside. If you're on a Mac, you can use it on an Intel Mac, probably. Get an Intel machine. Sorry for that. I mean, this uses these SSE instructions, so maybe you get an SSE support library which supports the SSE intrinsics on a Mac, on an ARM Mac, something like that. I don't know. Otherwise, use an Intel machine. On an Intel machine, it works. Use a Unix, Linux machine, it even works better. Here I have a little introduction how to use this, so it's already written here, so it uses these intrinsics. So if you have a machine which doesn't support this, I'm sorry for you, but yeah, okay. What you need is basically these support libraries, so build essentials. Basically this gets compiler and all the stuff, and the LAPACK library in its development version, so that you can link and compile to it, and that's basically it. And then it's like one GCC call in order to calculate to compile this C file here and get this thing running. So let's do this. So of course I have all these dependencies. If you don't have them, if it doesn't compile, you just go here, you copy this into your terminal. If you're on an Debian based machine, Debian based machine means you're on Ubuntu, Mint, Debian, of course, and whatnot. If you have a different distribution, you need a compiler, you need LAPACK development library, that you have LAPACK headers basically in your system, so that you can link against the LAPACK library. You don't even need headers, you just need to link against the LAPACK library. Okay. I mean, probably other people on different distributions, they will know how to get to the dependencies. That's the way you compile it. Here on my machine, all the dependencies are installed, so I don't do this. I just will get this tool here. So how do you get this? You copy this here. There's the git command, so use git clone and you get the little tool here. Okay, so we have our tool, and here we have PDB normal mode analysis. Nice, no? Okay, so let's get into this folder and compile this. CD into the folder. Then I told you here we have the compile command, so we copy this here, no? That's the compile command. Let's copy this. I don't know, I copy it like this too. I don't know. Yeah, this works. Copy paste it here. And we compiled. And we have the NMA tool, no? NMA. And you see, so that's what we want, no? Okay. So what do we need? A PDB file or XYZ file. So XYZ file is something that you can craft by hand, where you basically can use this normal mode stuff. So you basically put in there just like a atom description and XYZ values. Here I'll show you how it works for a PDB file. Way more interesting, no? You know, the RCSB PDB database. So from there we can get these molecular structures. So RSCB, PDB. That's database, and we will look up for a random protein and try this out. So what can we try out? A protein that I've worked lots of on is like thrombospondine. Okay, thrombospondine, I'm in there. Let's see what we have here. Thrombospondine structure attributes. We don't find it. What is this crazy stuff here? Thrombospondine. Because with TH, no thrombo. Spondine, yeah, 1. That's what we want. Not this one. Maybe this one. No, that's a cool one. 1UX6, no? Let's get the normal modes out of this here, no? So I download this here. Lots of ions, but forget about the ions right now. We just want to have these normal modes here, and we download this molecule, download files, and you see how this can move here. So PDB format, that's what we need, PDB format, and we need this VMD tool, but VMD is a program. I already downloaded a lot of proteins, basically I have this here again, I don't care. It's in my downloads folder, but we also need this VMD tool. So VMD, so in order that we can visualize the movements, so VMD, you can get this VMD download, something like this. And so it's this website, it's ksuiuc.edu. They have a slow website, so you click on this, you register with them. It's free. No, they have a crazy license, but you click on there, you register with them, you download this. Basically, the Red Hat version, it works on the Ubuntu, Linux, and whatever. It works on other distributions. You can download just this and install this. A bit complicated to install, but you will find it out. You just go with the instructions that are on the website. And or talk to your system administrator, because it is so that you can install this on your system. Here we have it installed. This different topic on how to install VMD. So on this machine it's installed. You have VMD, and we have here this Visual Molecular Dynamics tool. It's a bit small because it doesn't really support high DPI screens as I have, but that's an inconvenience that we can live with right now. Okay, so let's calculate normal mode analysis, and you will see how easy this is. So NMA downloads. Okay, my file. So my file is here. Downloads. I have to calculate NMA. Just let's see what we need here. So NMA, we need a PDB file. I need to tell him what file type I have, what spring constant I need, cutoff. So spring constant is, of course, I have 2 atoms, and basically how strong they interact. So it's like if I close them up, how strong they will push away, or if I pull them out, how strong they will pull back. The spring constant. Cutoff, it means how many springs I built. So if I'm here and I have like 15 atoms around them, and I put the radius around this, and I built springs in my network here, in order to modelize this molecule. But if the other atom is very far away, then I don't want to build a spring up there, because it will be connected anyway by other springs. And so you have this cutoff. Well, from this atom, how many other atoms do I build a spring? That's the idea here. I put 15 in there as a pretty nice value. It depends on and then highest mode to be visualized. So it starts at 7, because it's like the first 6 there. Don't mind. They're like the how do you call it, translation and rotation. And translation and rotation for normal modes is of course 0, and because we only want to have these internal motions, of course, of our protein. That's the way it is. And so here you say, for example, 9 in order to get the first 3 modes out of, let's say, 10, first 4 modes. We will do it that way. And let's get started, no? So what is a nice spring constant? I get 0.5, no? What did I use last time? I don't remember, but let's say, I guess 0.5 was a nice value, no? If it's too hard, then it doesn't really move, so you need a little playground here. Let's see what I'm using here typically. What do I suggest you on the GitHub page? Okay, on the GitHub page, what do I suggest you? 0.5 here. Oh, missed it. I should write here PDB. I will fix that later. So 0.5. Let's try that out. Anime. We downloaded our PDB file here. Downloads. This one UX6 PDB file. Let's visualize it before. We've already seen it, I guess, in the PDB website. And it was this globe with this dog there, something like this, no? If I go here and get another stuff here open, let's do VMD downloads 1UX6. Yeah, that's what it looks like, no? So this is this whole protein here, no? You can do like this here, graphics and representations, and then you can say here new cartoon, and then you get the cartoon representation, and this is basically what it looks like, yeah? And we want to see how this moves, so we just take all the little alpha carbons and connect them with the springs and see how this moves, this complex here, yeah? Okay. Yeah. This molecule, no? Okay. So create this here. Okay. And then we have, so I said, what do we need here? File type. So we have the file type. This is a PDB file, no? Yeah. Spring constant. So I said 0.5. Cutoff 15. Yeah, 15 is a nice value for a cutoff. 15 angstrom or something like this. Yeah? And then highest mode to be visualized. Well, 10, so let's get 4 modes, no? From 7, 8, 9, 10, 4 modes, okay? Let's do this. Now let's run this. And you see it takes a bit of RAM, it runs here, and we finish this, no? And right now, if I go here, I have my 4 modes, so 7 mode, 8 mode, 9 mode, 10 mode. And I can go here in VMD in, let's say, the first mode of this, no? 7 mode. And then I see something like this, which resembles, of course, my molecule, but you just see these little points, no? It's not very interesting, but if you go here, graphics, representations, and you go here, draw, van der Waals. So this is basically the shape of our protein in this normal mode representation, no? So all the alpha carbons just now. Yeah, and right now I want to see the movement, so if I go here, if I click here, I see that my molecule here shakes my this little part here of the molecule, and that the rest here stays almost fixed. So this is basically this normal mode calculation. So if I say, okay, this is the little movement, I want to have more movement, no? Let's have more movement, come on. So let's quit this here. Let's have more movement, so let's recalculate these normal modes and lose a, let's say, lesser spring constant, maybe 0.2. Let's see what happens. Just to get a bit of play with it, no? And so if we do this here and we get the 7 mode here, and we go again into our graphics representations to have van der Waals. Okay, and then we click here move. You see it moves a bit stronger, so you can the movements, as you see, the directions are always the same. Yeah, you can adjust the spring constants accordingly. So if it's too stiff, you loosen the spring constant. And what we see here is basically that of the protein. This part here will be very rigid. This here is also very rigid. What will be moving here is this little part here, which absorbs the energy first, no, something like this, no, which needs least energy to move. And so if we have this here, so this was the first mode, so let's get into the second mode. Normally the second mode is a torsion mode, so like bending, torsion, something like this, depends on the molecule shape, but that's the idea. So representations, van der Waals. And this here is our abstraction of the molecule again. If you want to see the original molecule, let's get the original molecule, come on. Downloads, so that you get an idea. 1UX6, no, that's what we run this on. So here you have the original molecule, you see it, yeah? Doesn't matter, so you can then basically interpolate these motions onto that, and so you get a rough idea about the motions of the molecule. And if I run right now my stuff here, right now I can't run this anymore because I have this one here now. If they have to got T over there, crazy stuff, but then I can run this, and I see that again, this little piece down here, so it's like torsion here, no? So the first was bending there, right now it's torsion, no? And so I can do this for each mode and see basically how it makes the molecule move. Yeah? Okay. I hope that's interesting for you. And this was our little normal mode tutorial on how to use this normal mode tool, so this PDB anime analysis tool. So where do you get this again? So you go here on GitHub, and you have here the address. So this is github.com/pdb anime analysis. I will put this into the YouTube link when I upload the video. And if you use my little tool here in order, together with VMD, as I've shown you, in order to derive, let's say, very quick rough idea on how your molecule will move and what kind of trajectory it will go into, then use this little tool, play around with it, use it on your own PDB files, and have fun with it. And well, I hope this was a nice tutorial for today. Thanks so much.